We've learned that we can use rate laws to calculate the rate of a reaction from the rate constant and the reactant's concentrations. Using calculus, we can convert rate laws into equations that'll tell us what the concentration of the reactants or the products are at any given time during the course of the reaction. These are called integrated rate laws. This is the integrated rate law for a first-order reaction, one whose rate depends on the concentration of a single reactant raised to the first power. We can relate the concentration at the start of the reaction at time 0 to its concentration at any other point in time. Note that this equation has the form of the general equation for a straight line. Y equals mx plus b, where m is the slope, b is the y-intercept of the line. So we can use this equation to verify if a reaction is first order, as well as to determine its rate constant. Graphing the natural log of A versus time will give us a straight line. A reaction that's not first order, then, will not yield a straight line. The transformation of methyl isonitrile to acetonitrile is a first-order process. Both of these compounds are isomers, molecules that have the same atoms that are just arranged differently. This kind of a reaction is called an isomerization reaction. Since both species are gases, we can take a look at their partial pressures over time. So you can see how our reactant's partial pressure, the methyl isonitrile, decreases over time as that reactant is converted into our product. And as you can see, graphing pressure versus time gives us a curve. But if we graph the natural log of the pressure versus time, for a first-order process, we get a straight line for a first-order process. We can also determine what our rate constant, or K, is from the graph by taking the slope of the line. Since the slope is the equivalent of the value for the negative K, we can take the negative slope to determine the K, or the rate constant. A second-order reaction is one whose rate depends on the reactant concentration raised to the second power. Or it could also be two different reactants, each raised to the first power. And the integrated rate law for a process that is second order in reactant A would look like this. So then, for a process that is second order in A, if we were to plot the reciprocal of the concentration of A versus time, that would give us a straight line. So then graphing the data is a second way of determining order of reaction. Here we have the chemical equation that represents the reaction of the decomposition of nitrogen dioxide. If all we're given is the time and the concentration of our reactant, then we can use graphing to determine if that reaction is going to be first or second order in nitrogen dioxide. Graphing the natural log of the nitrogen dioxide concentration versus time does not give us a straight line, so it must not be a first-order process. But graphing the reciprocal of the concentration of the nitrogen dioxide versus time does give us a straight line. So that tells us that the reaction is second order in nitrogen dioxide. The half-life of a reaction is the time that it takes for half of our reactant to react. Or in other words, the time that it takes for our reactant to reach 1/2 of its initial concentration. And so in this example, the half-life of our compound is 10,000 seconds, because that's the amount of time that it took for half of our reactant to be consumed. Half-life can be important in a few different areas. For example, in pharmaceuticals, it would be important to know what the half-life of a particular drug was so that we would know how long it's going to be effective for. By rearranging our integrated rate law for a first-order reaction, we can obtain the equation for determining the half-life of a first-order reactant, where half-life is equal to the negative natural log of 1/2 over K, which is equal to 0.693 over K. Rearranging our integrated rate law for a second-order reaction will give us this formula. The rates of most chemical reactions increase as the temperature rises. You can see an example of that with these light sticks. The light that's in the hot water is glowing more brightly than the one that is in the cold water. The rate constant, K, is temperature dependent. So it's really important to remember the only thing that will change the value of K is temperature. Also, since K is temperature dependent, if you see a value in a problem, it's always going to have a temperature attached to it. So don't be confused and think that you necessarily need to use that temperature. It's there to show you the conditions and what the value of K will be under those conditions. In a chemical reaction, bonds are broken and new bonds form. Molecules can only react if they collide with each other in the right orientation and with enough energy. And by correct orientation, I mean the molecules that need to bond need to be lined up with one another so that they can collide with each other, with enough energy to cause bonds to break and new bonds to form. In other words, there's a minimum amount of energy, or activation energy, that's required for the reaction. Here's an analogy. If you don't hit the golf ball with enough energy, it's not going to have enough energy to get up over the hill. A chemical reaction won't occur unless the molecules have enough energy to overcome that activation energy barrier. Some chemical reactions occur all at once, but many of them occur in a series of steps. Each step is known as an elementary process or an elementary reaction. The molecularity of the process tells us how many molecules are involved in the process. A unimolecular reaction then is going to involve one type of molecule, maybe a decomposition reaction, and this is the rate law that would be written for that type of a process. A bimolecular reaction could involve two of the same types of molecules or two different types of molecules. And you can see what the rate laws would look like for that. And maybe you've noticed that if you know the molecularity of the process, that will also tell you what the order of the reaction is. Unlike the coefficients in the balanced equation, which do not tell you what the order of the reactant is. In multi-step reactions, the slowest of the steps is called the rate determining step. The overall reaction can't be any faster than the slowest step. These guys set a world record in the 4x4 in the Olympics a couple of years ago, but the time that they achieved as a relay team wouldn't be 36.84 seconds if it had taken this guy 36.85 seconds to run his leg. Catalysts increase the rate of a reaction without being consumed in the process, and they do this by lowering the activation energy. One way they do this is by holding the reactants together and helping to break the bonds. Here we have hydrogen and ethylene adsorbed onto a metal surface. The bond between this hydrogen molecule needs to be broken, giving us two hydrogen atoms. Find their way to the ethylene, and they bond to the carbon and form ethane, which is released. One of the most important examples of catalyzed reactions occur in the human body. Enzymes are catalysts in biological systems. And the chemical reactions that are occurring in our bodies have to occur at very specific rates in order for everything to keep working as it should. This is ground up beef liver. It acts as a catalyst in the decomposition of hydrogen peroxide, causing it to rapidly decompose into water and oxygen. The enzyme responsible is called catalase. You probably remember that enzymes end in ASE. We use something called the lock and key model to describe how enzymes work. The enzymes have specific locations called the active site where the catalysis will occur. The substrate is the substance that's going to undergo the reaction at this site. And although they call this a lock and key model, that's not really too accurate because this isn't really just a fixed form like this. It's something that changes shapes in order for this process to work. Once the reaction occurs, the products then leave, and that allows another substrate molecule to enter. And the process starts all over again.